Hello everyone, welcome back. This is RAD103, Module 4, Lecture 1.2, and we're in the middle of a discussion about geometric factors, and we're talking about object position now. Alright, so to start this lecture in talking about object position, we want to make sure that everything is horizontal flat, so your image plate is flat, the body part that you're positioning is directly on it, parallel to it. And then your X-ray beam or your X-ray tube is perpendicular to those two objects. So that would be ideal. If you have any type of angulation of one of those things, whether it be the body part, the plate, or the X-ray tube, then you're going to lead to some sort of distortion. And in looking at these pictures, I like the picture over on the right a little bit better. Even if we just took the central ray right here, this primary beam coming straight down, you can see that the arrow is not parallel to the board. And so because of that, it's going to show a shortened image. If you measured from tip to the very back, it would not equal the actual measurement of the actual arrow. And so we end up with a foreshortened image. And this is showing a dramatic foreshortened image because the angulation is even more dramatic. Here's an example where you might end up with an elongated image, is that if we had the tube angled towards this direction, you're going to elongate that body part. And so once again, if you measured the actual image, if you measured the shadow here to here, and you measured the actual arrow, this image is longer than the actual arrow. So to remember that you want to have the body part parallel to the plate, and the beam perpendicular to those two items, that's when you're going to get the most true form of that image. If you start angling one of those things, then you're going to get some type of distortion. So let's start by talking about elongation. Elongation is when the anatomical part on the image appears longer than what it normally is. And a good example of that is something you've already learned, and that would be your scaphoid view. So if you took an image of your scaphoid with a straight PA shot, and you didn't have any angulation on the tube, the scaphoid would appear fairly normal size. There's no elongation to it. You did not distort the image. You might have a tiny bit of magnification, but like I said, you'll always have a little bit of magnification. But it's going to be a normal size. We angle the tube on purpose. We angle that tube to elongate the bone. And so that's when you get elongation. So your body part is parallel to the board, but you've angled the tube, and that's when you're going to get elongation. And so the image appears a little bit longer than the actual body part itself. And so here's an example of what I was just talking about. A straight PA view, there's no angulation of the tube. And then if we have a little bit of angle, roughly a 20-degree angle, and you've got that Alden deviation to get rid of any superimposition, you can see how this scaphoid is a little bit longer than this one. And so that's an example of elongation. And one more crazy example, you're going to learn about this next year at this time. This here is called a Towns view. This is of your skull. Now this is a skull with minimal angulation. For this picture, you actually do have about 15 degrees of angulation. But here you have about 35 degrees of angulation. And so you can see how that completely distorts the image. It's really taking the jaw. What this image is for is it's a good view of the rami, which is this upper part of the jaw, to see if there's any fractures there. You can always make it up to the TMJ. But you can see how we've elongated that jawline, and so it's real easy to see a fracture. We're taking away any superimposition, where this has some superimposition right around here. You don't have it here. So just another example, we do elongation on purpose, and those are just two examples of doing that. All right, the other thing to discuss is foreshortening. And so instead of making the image longer, we're going to make it smaller than it really is. And so if we look at this top example, this is a scapula. So if we just took a scapula bone and we put it in the middle of our plate, we have a perpendicular beam, we would end up with a good representation of what that scapula looks like. So letter A is what a normal scapula would look like. Everything, parallel, perpendicular, everything we wanted. If we kept the scapula in the same position and we angled the tube and we took the picture again, we would cause elongation. So you can see that this portion of the scapula is now a lot longer than it was. You can see the bottom here maybe reaches about an inch away from the edge. Here the bottom is now almost going over the edge. So we've elongated, we've made this scapula longer, it's distorted. C is foreshortening. So what C is what we've done is we've put the tube back to perpendicular. It's now perpendicular right to the board, but we've angled the scapula, upward or downward. I can't tell from this angle, but we've angled it. And from that, we get a funny looking scapula because it's now foreshortened. The other example that I use to discuss foreshortening kind of brings up the importance of making sure that if you are doing an oblique hand and you need to see joint spaces, you must keep the fingers straight. Otherwise, if they're angled down towards the plate, you're going to foreshorten them. So these bones are shorter than they actually are. And not only that, you're also cutting off the joint spaces. I can't see the joint spaces anymore. And when we're dealing with arthritis, you have to see the joint spaces. So if you're the type of person who, just kind of does their oblique hand and their fingers are curled and they're going down towards the plate, you're going to foreshorten the distal ends of those fingertips. And so it doesn't look like much, but it's enough to throw it off. You're not getting a true representation of it. So that's what foreshortening is. Just remember, you have a perpendicular beam, but you've angled the body part to the plate. And so you are then going to get foreshortening with that. Now, I talk about this because it's in the book, but I find it's kind of silly. The shape of the object that you're x-raying, if it has a shape that matches the angulation of the x-ray beam, then you're going to have little to no distortion. I say that, but what body part or whatever we're x-raying is going to have the exact shape of the x-ray beam itself. But letter A, you can see it matches perfectly with the angulation of the beam. You're going to have little to no distortion at all from that. If anything, because you've got a high OID, you're going to have a magnified image. But for goodness sakes, what are we x-raying that's going to be like this? Nothing. Going back, though, don't forget, if you've got a thin body part, there's going to be minimal distortion. Okay, not too much. You are going to get a little bit of focal spot blur, and we'll talk about that in a little bit. And it's going to be obviously magnified because you're away from the plate. But because it's thin, as far as shape distortion, it's really not going to be too bad. This last shape, though, is kind of what we're x-raying. I can see maybe a person's abdomen like this, person's forearm, person's leg. We've kind of dealing with some round body parts or oval-like body parts. We certainly don't have anything with sharp edges that we're x-raying here. And so this is just letting you know we're always going to have some form of distortion and blur because of the shape of the object and because of how it interacts with the beam. And so the shape of the object can determine whether or not you've got some geometric distortion, but because of the body part shape that we're always dealing with, we'll always have a little bit of it in our image. Spatial distortion is any type of misrepresentation on the image of the actual spatial relationship amongst the objects. So that's a fancy way of saying, if we looked at how these objects truly are situated, object A, object B, we got two arrows, arrow 1, arrow 2, or A or B, whatever. You can see that there's two distinct arrows. There's two different arrows. But if we were to take a picture like this, we would end up with an image like this, where one is superposed over the other. You almost get this double barbed arrow. It's because one is superimposed on top of one another. And this is only a two-dimensional image. But it's for reasons like this that it becomes important to realize that we need two planes of view when dealing with X-ray images. Just getting one plane of view is usually not enough for most things. Of course, we only do one view pelvises. We only do one view abdomens usually. But when we're dealing with broken bones, we usually try to get two, maybe three planes of view in order to truly understand what's going on with the image. Let me show you an example. Here we have an elbow image. So you can see that the person has, it looks like an AP or maybe an externally rotated elbow. I can see a decent space in between the radius and ulna here, but it looks like an elbow. now that this second plane of view is shown, it really changes the story. That's a great example of spatial distortion. The first one almost looks like a normal elbow. You don't see much trauma going on to it. But that second plane of view really speaks volumes as to what that person's going through. And so doctors and radiologists have to be aware of spatial distortion. But you also want to make sure that what you're doing as a technologist can minimize that, or you're giving them a second plane of view in order to show them exactly what's going on. And with that, I'm going to stop here. So we still have some geometric distortion topics to talk about, and that'll continue on in the next video. I'll see you there.